Mobile phone performance have risen drastically over the last decade, with even entry-level mid-range phones offering very decent performance that you would have expected from flagships not so long ago. A large part of it has been the increase in processing power that's been afforded to phones with newer and faster SoCs, with much improved CPU and GPU performance to handle a wide variety of tasks, from browsing Facebook to playing competitive games in a device that can fit inside your pocket. Of course, these tasks have not stagnated either, and with the rise of processing power came the rise of much more complex applications designed to take advantage of these much more powerful devices. This has meant more demand in terms of raw performance, storage, and memory usage. Phones these days comes with 2 to 3 gigs of RAM as standard entry level, and 8 gigs is no longer uncommon for the mid-range. This is crazy to think about when you consider that this is the same amount of memory that mid-range laptops had to use just a few short years ago. And even if that won't be enough, which if trends continue, they increasingly won't be, there's one recent feature in Android that would allow users to extend their memory beyond what's physically present: virtual memory. Let's talk about how that works, what impacts it actually has on a phone's performance and multitasking abilities, and why it only got recently introduced. Before we begin, let's first have a primer on how data is organized inside any computer system. This is a storage pyramid, the most fundamental way in which data is prioritized to figure out where exactly to store them. The higher up you go, the more the data gets prioritized, which means that it gets to sit on a storage medium closer to the CPU and can be accessed much more quickly. But it also means that as the closer you go, the smaller the data that you can store due to the increasing complexity and costs of cramming data into spaces that are close and fast to the CPU. Here we can see that system memory, or RAM, sits below CPU caches and is where data that applications will most likely need gets stored from the next tier down: storage. This fact is central to understanding virtual memory. The more applications you have open, or the more massive and demanding they are, the more your system memory gets used up, until such time that it gets filled up and can't load any more data. This can result in a few problems. One is that the application you're trying to load will just crash due to insufficient memory, or it may not crash but run spectacularly slowly due to the device having to rapidly load data in and out of storage back into system memory. Or it could display some weird bugs, like not loading in some textures in a game. Whatever the case may be, it's not great when you run out of RAM to use. So a solution is needed: virtual memory. Now, the concept of virtual memory is far from a new idea. It has been a regular feature in PC for a long time now. For Windows, it's called page file, and for Linux, which is the bedrock of Android's kernel, it's more commonly known as memory swap. And of course, macOS itself also has features like this. Whatever it's called, the concept is fairly straightforward. The system will reserve a free space in your storage and create a partition which will be used to store, cache, swap, or page minor or inactive processes and applications in order to preserve actual system memory to demanding tasks or to avoid a total memory fill-up. As the name implies, this essentially extends the amount of memory a system has by using part of its storage as virtual system memory. Genius, right? A little too ingenious, you might think. If memory can be expanded by simply reserving some space on your storage, why do we still need these monstrous 8 to 16 gig phones when we can just extend them anyways? And if this technique has been in use in PCs for decades, why was it only introduced in Android recently? Well, there are a few very good reasons for that. Let's go back to the storage pyramid and remember that important fact I highlighted earlier, that system memory sits above and loads data from storage. What does that mean to this conversation, you ask? Everything. The reason why data is loaded from storage into system memory in the first place is that RAM is much much faster than storage. But more than that, it's also much lower latency. A typical NVMe SSD has latencies of around 50 to 100 microseconds, and that's ignoring other system overheads like the interface itself. System memory, meanwhile, has latencies of less than 100 nanoseconds. Nanoseconds, that's less than 1,000th of a microsecond. This means that RAM is orders of magnitude faster and lower latency than storage. And for a CPU that's handling billions of instructions per second, that makes a big difference. This is why CPUs don't just call up data from the storage directly, because it's going to be wasting CPU cycles just waiting for data to be sent to and from storage, which also wastes time and power. Virtual memory doesn't solve these problems. It's literally just storage used by the system to dump rarely used data and processes to prioritize more demanding ones. Now that is a benefit in and of itself, and having virtual memory to waterfall on when the system memory gets filled up allows applications to continue running instead of just crashing due to insufficient memory. But you will still be limited by the speed and latency of the storage medium, and it's still much better to just have more physical memory in the first place than just extending it with virtual memory. Okay, so virtual memory is not a replacement for RAM, but clearly it does have a benefit in allowing the system to store more data and run more applications in the background, as well as dynamically adjust them in order to properly prioritize things. So why did it take so long for Android to embrace this technology when it's been on PCs for decades? I mean, Linux, which is what the Android kernel is based on, has supported memory swapping for a long time now. So why didn't Android? Well, there's an argument of actual necessity. Recall that the data that's being loaded into RAM comes from storage in the first place. If that data isn't going to be prioritized and instead just gets put into virtual memory, you're essentially just dumping it back into the same drive it came from, just in a different partition. It's like taking water from one end of the pool, putting it back into another pool that then water falls back into the end of that same pool. You're essentially not doing anything productive. And for a long time, phones have not really had the necessary performance to conduct true multitasking, which makes this scheme of caching unused applications sort of moot. And while things have certainly changed, there's still the argument that this is not only unnecessary, but also harmful to the device's storage. In their developer page explaining how Android's memory management works, Google stated, quote, "On Android, storage isn't used for swap space like it is on other Linux implementations, since frequent writing can cause wear on this memory and shorten the lifespan of the storage medium." Sure, you might say, but why would it be an exception when PCs have been using this feature safely for a long time now? In short, because phone storage is different from the SSDs that PC users are much more familiar with. They're both flash storage, sure, but the grade of flash differs significantly. SSDs use higher grade NAND flash with much more powerful and versatile controllers that allow for higher speeds, lower latencies, and much higher endurance. Phones, by contrast, are constrained by both space and power, which means that they will have to use lesser NAND with controllers that are often just built into the SoCs for better efficiency and integration. This means lower overall performance, higher latencies, and less endurance than traditional SSD storage, or at least traditionally. The fact that this technology has been introduced and is becoming more widespread now may be due to a few converging trends in the industry. One is the explosion of memory usage by applications and the Android subsystem itself, which has also helped push the actual memory capacities of phones up significantly. And second is the maturation of phone storage, with standards like UFS guaranteeing SSD-like performance and endurance, which means that memory swapping won't be as slow and damaging to your device's lifespan as it once was. Realistically, this feature is meant more for lower-end phones with less system memory, as it helps avoid crashes due to insufficient RAM and allows them to handle more processes without crashing or slowing down too much. Of course, the bottleneck will still most likely be in the lower performance SoCs, but with enough optimization, virtual memory can at least mitigate the memory constraints on these budget phones and make them somewhat more bearable to use. Of course, for phones with much larger memory, this is less likely to come up, since the amount of memory itself can bear the burden of whatever application you throw at it. And at the end of the day, it's going to be the SoC that's the bottleneck. I still maintain that 8 gigs on a phone is overkill for the vast majority of people. Though demands do change, and in the future, the ability to expand that memory with virtual memory on these phones will help expand their lifespan as well, which reduces the amount of e-waste in the world and makes these phones a much better investment. So that's really it. The premise of virtual memory is very important in smartphones as a way to increase their versatility in the face of ever-increasing demands for performance and multitasking. More and more, phones are taking on the role of being the primary or only device of many people, and especially after the pandemic, the need for such a versatile device that you can use anywhere for any purpose is increasing ever by the day. Extending memory virtually is not and will never be the same as actually putting more physical memory, but it does help in situations where applications push your devices to its utmost limit.